Hello. In this lesson, we're going to work on some applications of logarithm properties. In the previous lesson, we did some, right? We applied the product rule or quotient rule to simplify certain expressions without having to use a calculator. And in this lesson, we are going to start with this very important property, which is right here, right? We talk about it at the end of the last lesson, so let's work on it again. Is that first we're gonna, get these properties, and some of these properties are very, very useful in the future, and it's, of course, is also useful for this course. And one of them is being b raised to the power log base b omega equals to omega. This property is something we have done before. And from the definitions perspective, right? The way we did it was from definitions perspective. So I want to give you these, how we derive it from the definitions perspective. And I also want to recap on the things that we did before to get to this point. Okay, so suppose I remove this, right? From this definition, we know that b raised to the power of triangle is equals to omega. A triangle is also the same as log base b of omega. So if I replace the triangle by its equal, and we will get that identity right away. What does this mean, right? What does this mean? What does it mean? Well, the meaning of this expression is actually very interesting. First of all, of course, we understand omega is going to be positive, right? Because this definition has indicated that omega is always going to be positive. It's a positive number, right? Positive number because it's in the domain of logarithm. Positive number is because it's the range of, the exponential, right? So if omega is any positive number, this omega can be expressed in exponential form of any base larger than 0, not equals to 1. So in other words, a positive number, right, which is larger than 0, can be represented by your chosen base in the form of exponential forms. And of course, the base has to be satisfying this condition, right? So any positive number can be represented this way. I know that's a lot to digest. Okay? In special cases, right? Say, omega, if base 10, then omega can be represented as 10 to a certain power. If omega can also be represented with e to a certain power, omega can be represented with base 2 to a certain power. You see, omega can be represented in all these different forms by different bases. You choose the base, right? Let me give you some other examples. For example, how would I express it? We just mentioned any positive number, right? Any positive number can be represented this way, right? So I'm going to take this one. Then you say, hey, let me give you a positive number and express it for me. Sure, I can represent 1, for example, as b to the power of log base b to the log base b of 1, right? And I can also use any base. right? I can use any base to say I can use base e, ln, and they are identical. They're the same value, right? I can also use base 10. I can also use base 10, that's a common log, right? So this is the meaning. Then you say, hey, you choose one is a very special number. How about you choose another number? Sure, I can choose, say 2.5. 2.5. How could I represent 2.5 with base, right? With whatever base, and I want to choose the base. And this number, of course, omega here is going to be 2.5, right? And any base you want to choose, as long as it is positive and not equals to 1, then I can represent it. So that's really what it means. Okay, so that's the meaning of it. Now, what we did before, we did the following. Okay, so this property is can also be seen from the other perspective, which we did before. What was the other perspective? In those perspectives, okay, we do this because it's very important for you to understand this aspect, okay? Say in that context, we say f of x is 2 to the power x in the case of base 2, and its inverse, okay, its inverse is log base 2x, log base 2x, okay? So with this said and done, we know that these two functions are inverse to each other. One's domain is the other's range, right? The domain for f of x is all real numbers, right? All real numbers, that's a domain. From negative infinity to positive infinity, that's a domain. And the range, right? The range is 2 to the power of x is positive, right? So how about log base 2x? What's the domain? Well, the domain is this input is positive, right? So the range here, greater than 0, is a domain. And the output, right? The output range, right, is all real numbers. So one's domain is the other's range, right? We understand, this is what we did before, f composite f inverse of x is equals to x. And this x, right, because f inverse is on it first, so this x is going to be from the domain of f inverse. And what's the domain of f inverse? X is positive, right? So x must be greater than 0. So this is true. And the other one is also true, is f inverse, right, composite f of x equals to x, but this x is from the domain of f, because f is on it first. So this x is going to belong to all real numbers. So even though they're both called x, but they're from different places. So they're merely placeholder, right? We know this is true if we have a pair of one-to-one function. So now we take this thing, right? And we're gonna plug in, we can just do it on the spot, right? We can replace f by it, right? So let's look at what is this piece, right? That is f of f inverse of x, okay? F inverse of x, right, which is f of f inverse of x. F inverse is log base 2x, log base 2x, okay? And then we're going to plug in the f, and then we're going to plug in the f, which is 2 to the power x, so we're getting 2 raised to the power of that. And that is equals to x from what we knew, so this is equals to x. Okay, isn't this what we got earlier for the base of 2? The only difference, we use omega here and we use x later. So they're really the same thing. They're really the same thing, right? So it was in this context we did that. And we can, of course, we can do the other one. We can do the other one. So what do we get for the other one? Okay, so this will be interesting to have, right? So we have all these very interesting properties. If you, when you watch this and you derive it with me, and you're gonna get better at this. But if you're only watching and not doing it by your hands, very soon you're gonna lose track. Okay, so please do pick up your paper, pencil, really go move along with me, and then afterwards try to do yourself. Okay, so the second part, let's see what we get. Okay, so this is going to be f inverse of f of x equals to, right? F inverse of f of x is 2 to the power x, 2 to the power x, right? And then if we plug this in for f inverse, right, if we plug this in for f inverse, what do we get? This is f inverse, right? So we get log base 2 of 2 to the power x. And that's going, of course, that's going to be x, right? That's going to be x. So we get these two very interesting, especially this one, very useful. And for base 3, same. For base E, it's also the same, okay? So for base 3, what do we get, right? Let's look at for base 3. Everything will be the same for base 3. Right? It's going to be 3 to the power x, domain and range the same, and base 3, that's the inverse. They're inverse to each other, domain range stay the same, and all we have to do is the same property. So what I'm showing you here is the same property for a pair of inverse functions. That's all. Okay, so still for E, let's look at the E. Right, let's look at E. We did this before, but it's very important that you can do it yourself. For E, that this is going to be e to the power x, right? So this is going to be ln x, right? And e to the power x, right? Only the base has changed. Wait, I think I put this should be base 3. Okay, I think I might have made a mistake here. So this is base 3. Okay, sorry about that when I was in a rush. And so this is going to be ln x. So now this is going to be e to the power of ln x, right? You see, we got this form. So you can derive this totally by yourself to gain that, you know, ability to derive and derive more and getting better. Okay, so now let's summarize, right? So we have this identity, right? We have especially this one identity, very, very useful. And these identities, we've seen that earlier, right? We have seen this identity. And in addition, we have all of these, you know, properties. So with all of these properties, right? With all of these properties, okay, of logarithm. All right, I'm going to put all of these things here as a special case. Okay, as special case. I'm going to put these special case. You don't have to, you really don't have to memorize these, okay? Unless, well, I'm not a big fan of making you memorize things. Right? I really want you guys to do it. And so if you need to watch it over and over, do that. Okay. So with all of these said and done, we have these tools at our disposal, So let's see how we're going to use it. right? Let's see how we're gonna use this. Okay, so I'm gonna put this together and I'm gonna put away. I'm gonna look at some examples so we can use these properties. We can use these properties, right? We can use these properties. The first set of properties, right? So we haven't reviewed much, is about using this piece in its various form. Okay, so let's look at example number 1. Okay, and here we have an expression. Okay, we are asked to evaluate. Okay, without using a calculator. Without using a calculator. Okay, so the expression is 3 raised to the power of log base 3, and then 5. What would this be equal to? Well, we can apply this property. We can apply this property, right? The base is 3, B is 3, right? So whatever omega is here, as long as we make the match here, and omega is 5, so the answer is 5. You see how easy that is, right? Let's look at example number 2. Still evaluating, right? We have a E raised to the power of ln of 5. What would that be equal to? Well, you can quote this property, right? You can use this property, and that's 5, right? That's 5. And example number 3, okay? And we have a situation that we're going to have E raised to the power of ln of square root of 3. And what would that be equals to? We use the same property, and the answer is square root of 3. You see, we just apply the property, right? Number 4, right? Number 4, we have E to the power of ln of pi. What would that be equals to? Equals to pi. Yay. Easy, right? Easy. So let's look at other examples of applying the product rule and quotient rule. Okay, product rule and quotient rule. Okay, so let's look at, we'll still express it precisely, still evaluate it without using a calculator. So getting a precise value, right? So I'm going to put the title over here and putting all of these properties actually after our current example. So this way they will always follow us, right? They will always follow us. So if for our reference, right? For my convenience, it's also for your convenience. But soon enough, the hope is that you don't need to look at those formula anymore. You can just practice, you can just do it, right? For example, we have a example number 5. Okay, we have a log base 2 of 6 minus a log base 2 of 15 plus log base 2 of 20. Okay, so it seems that we have product, quotient, we have both. So which one shall we use, right? There are multiple ways to do this, actually. There are multiple ways to do this, right? You can combine these two, right? And then after you combine these two, you combine all, the result with the last one. Or you can regroup, you can put these two together right? And then do subtract. You can use a, you can move terms around. You can move terms around. But if we don't do anything of moving terms around, we just follow whatever it is given, right? So you can get the quotient rule, right? So the quotient rule in this case is going to be from right to left, right to left, right? So if you like to write it this way, right to left, you can just put the left on the right and right on the left, right? So that would do. And our base here is 2. Okay, so this is just our little node, right? This is just our little node. And now we have a 6 and we have a 15, right? So A is 6, B is 15. And here you go. So these two, by quotient rule, we got that. And of course, still plus log base 2 of 20, right? And then what? We're going to put these two together, right? Because ultimately we want to simplify this without using calculator to see if we can simplify it. Okay. And now we can bring the product rule to our rescue, right? So product rule. For product rule, we're really doing it from right to left. So we can bring this thing. It doesn't matter really, but it's just more to our habit, right? So right to left, right? Our base is 2. A is 6 over 15, right? A is 6 over 15. So A is 6 over 15 and B is 20, right? So B is 20, right? So treat this as our scratch paper, right? You have a scratch paper. So in the end, we get, well, we're not to the end, we're almost to the end. We finally combine them. And let's simplify, right? So base is B, so we need to change that base to B. And let's simplify this expression, right? And what do we get? Inside the parentheses, can we reduce it? Of course we can, right? 20, 15, right? 20 divided by 5, we get 4. 15 divided by 5, we get 3. And 3 divided into 6, we get 2. So this is 8, right? 8 is 2 to the power 3. And so in the end, in the very end, our answer is a 3. So these practices is really try to get us to be very familiar with the properties, with the properties, okay? And of course, these are the scratch paper work. You can put it away or you can just leave it, but you don't need to turn in these, right? So when you show your work, and this is how much work you need to show. And maybe a little bit less, right? Maybe a little bit less because you could have reduced it here, right? You could have reduced it there. Of course you can, but I just didn't reduce it. I just put everything together and reduced it in the last, right? I just talk about another method which you can shuffle the terms. Sometimes it's actually bring you a lot of convenience to shuffle the terms. Okay, for example, I can shuffle the terms, right? So how do I shuffle the terms, right? I'm going to bring these two terms together, right? So I will have this question. I'm just going to move this subtraction part to the last. I'm going to bring it here. Okay, and then I'm going to, for some of you, right, which you're getting better at this, you can just go straight to log base 2 of 6 times 20, right? 6 times 20, right? And divided by 15. You can totally do that, right? And this is to multiplication divided by 15. So you got that. That's using quotient rule a product rule and quotient rule, right? All at once, and you're gonna get the same answer. Surely you're gonna get the same answer, okay? So you're gonna get the same answer, precise, for sure. There you go. So you can show your work this way. Okay. So usually the way to show work is not unique. So let's look at another one. Example number 6. Okay. And this time we have a log base 3 of 100 minus log base 3 of 18 minus log base 3 of 50. Okay, log of 50. There are many different ways to do this. Okay, method 1. Okay, you can actually turn off or just pause the recording and try your own before you see my answer. Okay, before you see my answer, I'm going to show you more than one way here. Okay, I'm going to show you more than one way here. So first way, I can go by the order. Okay, but I'm not going to go by the order. Okay, I'm not going to go by the order. So what I'm going to do is that I'm going to subtract. You see these two terms, I'm going to pull out the negative sign. So I'm going to insert parentheses. So this piece, adding that piece. These are purely algebraic manipulation. And for you have reviewed algebra at the same time. Okay, so subtracting parentheses, right? Subtract, so we can subtract the parentheses. So inside the parentheses is going to be adding. Adding means we're going to use the product rule. So inside we're going to use the product rule. So we're going to log base 3, right? And we have 18 times 50. Okay, I'm not in a hurry to calculate this product because I know there's a quotient waiting for me, right? Product rule, quotient rule, right? So I'm going to use the quotient rule right next. I think it's usually save time not to be in a hurry to calculate, every multiplication or whatever. Just wait until last. Now I'm going to reduce it. Okay, now is the time. I'm going to reduce the inside before logarithm takes effect. So I just reduce it, right? 50 divided into 100 is 2. 2 over 19, 2 over 18 is 1 over 9. 1 over 9, so we're very close. And 1 over 9 is 3 to the power of -2. So in the end, the answer is -2. Finished. Okay, of course, this is one way to do it. Another way you could do it. Okay, another way you could do it. Okay, let's look at method 2. Method 2, you would just do straightforward. You could just straightforward. Okay, just do not do anything. Just do it in the order it was given. Okay, so in this piece, okay, I will have log base 3, not 2. Okay, so quotient rule. So we're going to take 100 divided by 18. Okay, and then we subtract that piece. And then we're going to apply the quotient rule one more time. So if we apply the quotient rule, okay, okay, this piece is a capital A is in the numerator and 50 is in the denominator. So we need to simplify this complex fraction. Okay, how do we simplify this complex fraction? Well, you're going to multiply 18 on top and multiply 18 on top. You can reduce it. Okay, you can reduce it. You know, we didn't reduce it here. We could have reduced it. Okay, well, we didn't. And then over here, what do we get? Right, what do we get? We're going to have a reduced form. 18 and 18 reduced, so the top is just 100. And we're back to over here. See, we're back over here. So the rest is going to be the same. The rest is going to be the same. I do want to show you the third method so that method 3, because I think the third method is also worth noting. Is also worth noting, all right? Because it's about using, okay, hold on. Okay, the third method, it's worth noting because you either do this from left to right or right to left. Okay, it's our choice, So what we can do is that we can break these into smaller pieces, and maybe we have a cancellation, right? We can have a cancellation. So log base 3, right? 100 can be written as 50 times 2, right? 50 times 2. So how about we have 50 times 2? Oh, hold on. I think I'll just make a different row. Okay, make a different row. So we still keep that 100. Okay, so I break that, right? And 18, I can break it down as 9 times 2. Okay, 2 times 9, right? So next, we're going to apply the product rule, right? We're going to apply the product rule, just like here, left to right. Apply product rule from left to right. You see? And then what do we have? We're going to have log base 3 of 50 plus log base 3 of 2. And you already see a cancellation, right? We already see a cancellation, but that's continue. Minus, and this piece, right? I'm going to put it in the bracket. So this piece is going to be log base of 3 of 2 plus log base 3 of 9. And the last, of course, subtracting log base 3 of 50. And here we go, we have a cancellation. This makes 0, right? That makes it 0. So that makes 0. These two are gone. So what do we have left? We have these left. And then we want to open the parentheses, right? If we open the parentheses, right? And that's going to be minus. And these two are gone. So in the end, we get negative log base 3 of 9. So this is going to be negative 2. You see, another way to do it. And there are ways in between. Okay, so try it and practice it. Okay, the key is get your hands dirty, get your hands on. Okay, the hands dirty is really, you know, it's not really hands dirty, but you really get busy to do it. I'm going to give you a couple more interesting, maybe a little more challenging questions, Okay, so that was our example number 6. Let's look at example number 7. Okay, this one, we have a negative 1/3, right? We have a negative 1/3, and then log base 3 of 27. Oh, 27, sorry. Academic questions, okay? Don't forget, you are dealing with most of the time academic questions. Not really question from the real world, okay? So the numbers usually are fairly neat. So when we work this question, right, we could apply the order of operation, right? And the negative third is outside and this base 3. And so this is going to be times 3. So in the end, we get -1, right? That's pretty straightforward. And let me give you some other interesting questions. Well, log base 5 of square root of 5. What would that be equal to? Well, we have log base 5. Right here, root 5 is 5 raised to the power of half. Okay, so the answer is going to be half. All right. Now, example number 9. So you may have noticed that these requires us to be more proficient with exponents, okay? And this exercise will show you that, right? So log base 5, okay, 1 over square root of 125. There, right? So what do we get? Okay, what do we get? I'm going to show you a different way to do it, okay? Now, when working with these exercise, one way to do it, it just works straight to it. Okay, you just work straight with it. And over here, you have to express, you try to express this guy, right? So what do we try to do? What we try to do is that we try to express, okay, so I'm going to use this. We try to express this piece equals to 5 raised to a certain power. So that's what we try to get to. Okay, so that's what we try to get to. Okay, so for that purpose, right, we have to know how to operate with power. Okay, so 1 over 125, right? So what we have here is we can write 125, right? We can write the square root of 125 raised to the power of -1. See, we can do that. How about 125? Can 125 be expressed at certain power? Yes, it's a 5 to the power of what? To the power of 3, right? 125 is 5 to the power of 3, right? 5 times 5 times 5, 3 times. 5 times 5 is 25. 25 times 5 is 125, right? So we have all these powers. So the half, the square root, right? So for the square root, we're going to convert that to power. And that's going to be the power of half. So this is the sequence of conversion. And then we just multiply these 3 powers. We multiply that 3 powers, right? So 3 times half, that's a 3 half. 3 half times -1. So we get in the end, what do we get? -3 half. -3 half. So the answer is going to be -3 half. If this looks a little strenuous for you, right? So let's try another method, right? So I'm going to give you another method. And this method might be something you have learned before, because I've seen that being used a lot. Some people like to use it this way, okay? But you must express it properly though. Okay, I saw lots of mistakes expressing it. So we don't know the answer, so we assume the answer is X or whatever symbol you like, right? So if I'm gonna use a crazy symbol, I'm gonna use, so how about I'm gonna use a crazy symbol like that, right? Well, by definition, this is the definition. This is the definition. So by definition, what does this tell us? This tells us, right? You can see base B, B is 5, right? B is 5. Omega is this piece, right? And triangle is the heart. So on this side, it's going to be 5 to the power of the heart. And that should equal to the omega. So this is the omega. This is omega. If you choose to do it this way, excuse me, you have to express it properly. And I'm showing you the proper way to write it. And these things are kind of scratch paper, okay? Kind of scratch paper thing, okay? So this is my think out aloud. This is my think out aloud. Okay, so I have a piece of scratch paper with me. So from here, you still have to work out the 1 over square root of 125 into power, right? So you have square root of 125 to the power of -1, right? And then you can express 125 as 5 to the power 3, right? And you will also get to the same place, really. And that will be to the power of 2, to the power of half. Oops. To the power of half. You cannot avoid that. You cannot avoid that. Okay, so in the end, you're going to get 5 raised to the power of -3/2. Oops, sorry. This is 3. This is 2, sorry. This is 2, and that's 3, and there's a negative sign in front of it. Okay, and then you compare 5 to the power heart and that piece, and the heart is what? The heart, right? The heart is -3/2. And it will be best if you tell the reader, right? This piece is equals to the heart, and the heart is that piece. Okay, about the expression of these kind of process, right? This is pretty standard, okay? Yeah, so this is how you would express it. You use definition, and then you still have to work out the exponents. You still have to work out the exponents. Okay, so let's look at another. We have layers, and we are at example number 8, 9. So let's look at example number 10. Okay, so this time you have layers. Log, common log of log and 10 raised to the power of 10,000. 1, 2, 3, 4. Okay, equals to. In this case, what do? We do it from inside out. We do it from inside out. So the outside waits for the inside getting simpler. And on this piece, log base 10 to the power of 10,000, and that's just going to be equals to 10,000. And 10,000, right? 10,000 is 10 to the power 4, 10 to the power 4. So the answer in the end is just going to be 4. Right, so layer by layer, we get to that. Let's look at another one. This one surely will get your attention. Okay, so what do we have here? What we have here is ln of ln e raised to the power e n to the power of 200. Look at that. What do we do? What do we do here? Still inside out. Okay, so the ln is going to wait outside. And inside, when we are handling this, we look at this is the base, and that's the power. So this piece is the power. Okay, this piece is the power. So inside, okay, we're going to get e raised to the power 200. So we're really using this property. Which property? Let me show you. Right here. We're really using this property. We're really using this property. Okay, we're really using this property. And under the e. Okay, for e. Right, so whatever is in the power is, you see the power here is e to the power 200, right? So that piece is the power, that's and the capital A, right? And ln e is 1, so we get to this piece, and then what else we get? We get 200, sorry. All right. Let's look at another one. Let's look at another one. EX 12. Example number 12. This one is e raised to the power of -2 of ln 5. Can we apply this property yet? Right? Can we apply this property yet? We cannot, because e raised to the power ln omega, the number before ln has to be 1, and here we have a -2, so we cannot apply this property yet. So the power to e is really -2 multiply ln 5, but we can use the property, we can use this property. Okay, so let me write it down for you. Okay, base raised to the power of m, and then to the power of n is equals to b raised to the power of m times n. So our m is -2, our n is ln 5. You can do any order you want. So you can put the n inside, m outside. It makes no difference. Okay, it makes no difference. But anyway, so we're gonna have e to the power of ln 5, and then to the power of a -2. Right? So when you multiply these two powers, like we have it here, you're gonna get back to where we started. Okay. Now for the inside, we can apply this property. So that's going to give us 5. So the inside of the parentheses is going to be 5. 5 to the power -2 is going to be what? Is going to be 1/25, right? So, sorry. Okay. The last one is going to be a little challenging. Okay. Example number 13. Okay, this one, I put this one on exam some in the past, and it has been pretty challenging for our students. Okay, so we have log base 2 of 7. What does that equal to? What does that equal to? Can we apply this property? right, for base 2, right? We have for base 2. Can we apply this property? Think out loud. Could we apply this piece? The answer is no, because these two bases has to be the same, right? The exponential base and the logarithm base, they have to be the same. And we have half and we have 2 here. So what do we do? Well, this piece is actually as an exponent, right? It's really an exponent. So if we apply this property, okay, let me tell you which one, right? We have capital A divided by capital B inside the parentheses raised to the power of n. What does that equal to? It equals to capital A raised to the power of n and capital B raised to the power of n, right? And what is our n? Our n is this piece. So A is 1, B is 2. Capital A is 1, capital B is 2. Do you follow me? So this is 1 and that is 2. And our n, so this is 1 to the power of n, 2 to the power of n, and our n is really this piece. You follow me? So our n is really that piece. So that is n is replaced. And the top, of course, equals to 1 always. So the next step, when we apply this rule, we get to this piece. The bottom, we're gonna apply this piece. Okay, we're gonna apply this piece to the bottom. Okay, and the top, 1 to the power of anything is still 1, right? And what do we get in the bottom? We get in the bottom, which is a 7. So 1/7 is the answer. I do want to show you another way to do this because I believe you guys need some practice using manipulating with power. Okay, very important, very important. So what I'm going to do is that I'm going to do this. Okay, so this is the first method. The second method. The second method. Okay, so what I would do is that I know that there's a power here, but I'm going to rewrite it to 1/2 as 2 to the power of -1. So then we're in a situation that we're going to multiply these two exponents, like what we did here. Multiply the exponents. Okay, so what do we get? We get 2 raised to the power of what? Negative log base 2 of 7. Can we apply this thing here? Can we apply this thing here? No, because we cannot have a negative sign in front of it. But can we bring this negative sign inside the logarithm? The answer is yes. What tool do we have? This piece. This piece, the power rule. Okay, so on this piece, okay, we're gonna work on this piece. We're gonna bring the negative signs, right? So we have a negative sign, log base 2. Okay, so the negative sign basically is the power, right? The base is 2. And the power, this is negative 1, right? So this was a triangle before. Hold on. This was a triangle before. So base 2, right? So we have a -1 here. So this is going to be -1. And what's a capital A? Capital A is 7. Capital A is 7. You see that? So, and the -1 times that, you can just remove the negative sign. So the power part is really equals to this piece. So that on the next step, I'm going to write it as 2 raised to the power of this piece. Can we apply this property now? Yes, we can. Okay, 2, okay, log base 2, omega is 7 to the power of -1. And therefore, the answer is just 7 to the power of -1. And that, of course, is equals to 1/7. That equals to 1/7. That's it. Okay. So this is probably one of the hardest question there is. Okay. And we do have a few more. Okay, I think we do have a few more. Since we are doing it, I would like to just bring it up. Okay, just bring it up. You get a bunch of homework to work with. Okay, and let's make this number 14. Example number 14. And this one we are doing is also making us to work with the power more attentively. Okay. All right. Well, no calculator. What do we do? What do we do? Right? So we want to, right? We want to express square root of 2 in terms of 4 raised to a certain power. That's what we want. That's what we want. If we can do that, and then question is solved. Question is solved. Can we do that? Right? Can we do that? Of course we can. Okay. Remember, any positive number can always be expressed in terms of a base b between, greater than 0, not equals to 1, and to a certain power, right? So we actually have those as our, so this piece is a guarantee that can be expressed any positive number. It's just in real application, right? You just have to work a little harder for it. So 2, right? Square root of 2 is really 2 to the power half. 2 to the power half. Okay. Now we are a little bit closer to it, isn't it? Because we need to express 2 in terms of something. Remember, 2 is square root of 4. Okay. So if we take a 4 to the power of half, right? 4 to the power of half. Wait. Do this. To the power of half. Okay. This is a 2, right? This is the 2. 2 to the power half. And so 4 to the power half is 2. So we have it equal. So in the end, we just get 4 raised to the power half, and then raised to the power half. The half times half is going to be a quarter. So it's going to be 4 raised to the power of a quarter. Right? And so the answer is a quarter. The answer is a quarter. I can see that some of you may like to do it the other way. Okay, using definition. Okay, I can see some of you may like to do it this way, which is fine, right? You are going to introduce a symbol. Say this time I'm going to use spade, right? And by definition, so let's bring the definition with us. This is our definition. Okay, don't we love our definition? Our definition is very, very useful. Basis 4. Basis 4, omega is square root of 2, right? So this is square root of 2. That's for omega. And that's for omega, right? And triangle is something we don't know. So we use spade. Well, let's use triangle anyway, though. Let's make a minimal change, right? So by definition, this piece implies this piece. Okay, so we're gonna bring that over. And then you're gonna have to manipulate root 2, right? And what is root 2 equals to? It's 2 to the power of what? Half. The same drill, right? And then you're going to work on the 2 to make the same base, which is 4, right? So the 2, with the 2 we have inside, we're gonna make it to be 4 to the power of half. Square root of 4 is 2, right? So you still get to 4 raised to the power of a quarter. Multiply half with half, right? So now you have 4 to the power triangle, 4 to the power quarter, they're equal, therefore, the triangle is, this triangle is going to be equals to this power 4, 1/4. It equals to a quarter. And there you go, finished. So the answer, right? So I put this as think out loud. Okay, no need to show. So just to wrap up, right? So this piece, you would just tell the reader that piece is equals to quarter. Well done. Okay. I think that's all for this lesson. That's long enough. So you should be able to do the homework. Okay, practice on the homework and get ready for the quizzes, is because you will be assessed. Okay, thank you for watching. If you have any questions, please send them my way. And thank you for watching.